Okay, so I've got a minute after 12. You heard the recording in progress, so I think it's time to go ahead and get started. Hopefully folks will continue to join over the next couple of minutes as we get rolling. But hello and welcome to the Chesapeake Stormwater Network's 2022 webcast series. Today we are going to have a great presentation on how many events you need using a data-informed approach to developing a monitoring program. So we'll go ahead and get rolling here. I just have a couple of introductory slides to kick things off, starting with our regular housekeeping. So we do have a couple of poll questions at the beginning just to kind of get folks oriented to the webcast, kind of so we can figure out who you are and what you're interested in as we're here today. If you're watching with a group, I know some of you that are back in the office now can watch these in a conference room or whatnot. So you can just select the option that best represents your group as a whole. We will do questions and comments. You can put them either in the chat box or the Q&A box. Either one is fine. I'll be keeping an eye on both of those. So anytime throughout the presentation, both Bridget and Elizabeth have indicated that they're fine. If you have something for clarification, you can go ahead and drop it in and they'll take those as we go. We'll also have some time for discussion at the end. As you heard, we are recording the session, so we'll have it up on our website in the archives probably in a day or two. We'll be able to get those up there along with the copy of the slides. And then finally, we do have a quick evaluation survey at the end. It's only 3 questions, maybe 4 questions. It'll take you less than a minute to fill out, but it lets us know that we're doing a good job, we're on track, and keeps our funders happy. For those of you who don't know the Chesapeake Stormwater Network, just my quick intro, please head on over to our website. You can click join, it's totally free. It just means you get our newsletter, keeps you up to date on all of these awesome webcasts, as well as any new fact sheets, resources, and our Best Urban BMP in the Bay Awards, which is coming up this fall, believe it or not, it's right around the corner. So we can get excited for that. You can also look forward to in the next month, we are getting our website totally rehauled. So you can go over and check that out as well. A couple of quick announcements about some other things that we have going on at CSN right now. If you have not taken it already, we would love it if you could take our biennial Stormwater Professionals Survey. This is a survey that we've been doing roughly every other year since 2011. So we have, about 10 years worth of data now, but it helps us understand kind of what your training needs are as stormwater professionals, what your needs are in terms of new resources and understanding. It helps us communicate to the large funders, EPA, NIFWIF, and others in the Chesapeake Bay, kind of what your capacity needs are as well. So this is all helping to inform better programming from us, as well as kind of keep the big funders that can get you the money up to date on kind of what your needs are. So I encourage you to take it if you have not already. It's a little longer than some of our regular surveys, but SurveyMonkey assures us that you will complete it in 10 minutes. Apologies for the car horn outside the window here. But we do also offer a $100 raffle for a gift card for if you complete it, so you get a chance to win that as well. So we have the link there. I'll drop it in the chat box later as well. We do have 3 more webcasts coming up this month, 2 in our campus stormwater series. So we are going to be joined by the Director of Sustainability at UMBC to talk about efforts that they're doing on campus to address climate resilience. We are also going to hear from the facilities team at Old Dominion University to talk about maintenance demands on campus with their stormwater infrastructure and sort of how that's changing and growing. That obviously will have a climate focus as well, as they're dealing with sea level rise down at Old Dominion, which is impacting the maintenance of a lot of their practices. And then we also have one at the end of this month on bioretention design adaptations for a changing climate. So really excited about each of those. You can register for those. Again, they're all free if you've not done so already. And then finally, this is just a quick teaser for a program that we are really excited to launch this summer. So this is kind of a keep your eye out, just another reason to sign up for the newsletter if you aren't already. But we're launching our Chesapeake Urban Stormwater Professionals Training Program. So basically, this is a brand new program targeting young restoration professionals. If you are sort of a junior, senior, or graduate student in college, or maybe you're in your first couple of years in the profession, maybe your first 3 to 5 years in the profession, and you would kind of like to bone up on some of your skills It's going to be a really flexible program. There are going to be 11 different courses covering all of the MS4 permit requirements, as well as some of the basics of stormwater and restoration practices, hydrology, the things that you really need to know. And you can do it at your pace. So we have these courses, but you'll have several months to complete them all. You can do them live, you can do them recorded, so just a way to kind of advance your career, expand your network, and earn a certificate along the way. All right, so that's the announcements. I'm going to go ahead and launch our polls for this morning or this afternoon. 2 quick questions just to get us started. The first is just to let us know who you're representing today. We like to know who we're talking to, who's in our audience. So if you're with a local government, state government, federal, private sector, NGO, academia, if none of those seem to match who you are, you can let us know in the chat if you think there's something better that represents you. And then our second question today, since we're going to be talking about monitoring programs and in particular for the performance of different stormwater BMPs, I just wanted to kind of get a sense of what pollutants you're most interested in monitoring for. So obviously in the Chesapeake Bay, there's a lot of concern for nitrogen, phosphorus, as well as sediment. But we're also concerned about a number of other pollutants in our urban environments, bacteria, heavy metals, PCBs maybe, as well as some other things. So if you're interested, you can fill out that poll. We'll sort of turn that around in just a second, but you can also let us know in the chat if you sort of fall into that other category. All right, so I will share that with you all. So it looks like we've got quite a few local government, about half of our audience today from the local government side, a few folks from the state side. And then on the pollutants, kind of predictably, a lot on the nitrogen, phosphorus, and sediment, a couple bacteria, and a couple others. So go ahead and turn that off, and then we can move right along. That brings me to our introduction. So I am really excited to have both of our speakers here today. Dr. Elizabeth Fassman-Beck with the Southern California Coastal Water Research Project, Dr. Bridget Wadzik from Villanova University. Thank you both for joining us. I'll sort of let you guys introduce yourselves because we can that way jump right into the presentation. But with that, I'll go ahead and turn it over to you to take it away and kind of get us into the bulk of our show today.
Well, thanks, David, and thanks so much for inviting us to talk to the Chesapeake Bay Stormwater Network. I may be in California now, but I've spent most of my, a very large chunk of my career, including graduate school, in the Chesapeake Bay area. So I'm a principal engineer at the Southern California Coastal Water Research Project. We are a special government agency. We do water quality research to support wastewater and stormwater dischargers and regulators. So basically, we're the research arm of a bunch of the very large public works departments and sanitation departments, as well as the state and watershed-based regulatory agencies here in Southern California. So basically from Ventura County down to the border of Mexico, like just south of San Diego. My research profile is all about stormwater BMPs, and in fact, I was followed an academic career for 15 years before joining SQUIRP in 2019. Go ahead, Bridget.
And I'm Bridget Wadzik. I'm at Villanova University, so I'm on the academic side of the house here. However, a lot of the work that we do with our group, we originated as what we call the Villanova Urban Stormwater Partnership, and now we have a larger umbrella organization that we are under called the Villanova Center for Resilient Water Systems. And with that work, it's very much in an application based perspective of always looking to see what our partners want. In the Villanova Urban Stormwater Partnership, we work a lot with our local governments as well as industry folks as well. And we've done quite a bit of work in stormwater sponsored by the Pennsylvania DEP with work kind of spanning across Pennsylvania. So even though Villanova is actually in the Delaware estuary, we are Chesapeake Bay adjacent and do have many of the same concerns. And so a lot of the work that we do kind of spans both of those water body systems. And I think where this work has been going and how we kind of got to this question, which we'll dive into here in a moment, is, we've been looking at these stormwater management facilities in a very sort of discrete way, but we're really kind of starting to move more and more into looking at an entire watershed and, how to be a good steward of the taxpayer money that might be going into it, the client money that might be going into it, and ensuring that we're actually, meeting target goals and doing them in a meaningful way. And this is kind of how this idea sort of kicked off for what we're doing, specifically talking about today, but I think in general, how Elizabeth and I both sort of conduct our careers and how we apply and discuss our research in these areas. So with that, we'll kick off. And Elizabeth and I have worked together. We've been friends for a long time. And so we often just have conversations about data, because isn't that the conversation you typically have with all of your best friends? And so we were working on something else. And, I, of course, am coming from the research perspective, where I have a whole bunch of graduate students and a bunch of research sites. And we're trying to collect a lot of data so we can report back performance over long periods of time to our funding agencies and then to our interested community. And Elizabeth has been working on a project, or a couple of projects through SQUIRP, where she's been working with municipalities about building out monitoring programs. And so as we were kind of talking about what a monitoring program should look like, of course, my inkling is to just say, get more data, get more, it's great. But how many events do you really need? Because monitoring programs are not free, and there's not a limitless supply of funding and resources for these monitoring programs. So that got to us really thinking about how many events do we really need so we can start making different assessments. And so we wanted to take a data-informed approach to this, as opposed to just using what's available, what's typical, but actually having data help us figure out what this monitoring program might want to look like. So Elizabeth, next slide, please. Okay, so just a little bit on some background, of course. So we do a lot of performance monitoring to help us figure out how to evaluate if one of our stormwater control measures, BMPs, GSI, whatever you like to call it, how they're actually working. And are they just in general performing well? And we don't really have a good definition of what that means. Is it meeting our downstream requirements, or whatever we are sort of regulatory wise trying to actually meet? So we can do a bunch of different types of performance monitoring, specifically where we're really collecting water quality runoff samples. So grabbing how much pollutant might be coming into our system, and then also looking at how much of that pollutant is making its way out of the system. We can look at this from both a concentration standpoint, and we can look at this from a mass standpoint if we can get flow monitoring in there as well. And so we're really looking at, doing a pretty discrete type of monitoring program, and one that can be, again, quite intensive from a labor perspective and from an analysis perspective as well. And one of the most common ways to, of course, do this type of performance assessment is we compare that inflow to the outflow, and we see, what kind of reductions are we having, how much of the pollutant is getting retained within the system, how much is continuing to make it downstream. Are we potentially a source as well of that pollutant? So these are the type of typical performance assessment that we're really trying to do. And we see that we're getting more and more of the requirement to actually do this. In my world, I'm looking at grant funded projects, and there's often the tie of having to have performance monitoring within those systems to prove that they're doing well. We also are seeing it more and more in permit compliance as well. You're starting to see in regulatory structures that there's a requirement to do some sort of monitoring. And often the language is quite like that, where it's like you have to do some level of monitoring. And there really isn't any guidance on how to do that. And then I'm also seeing some municipalities just taking some monitoring on themselves, because they want to make sure that they're putting in maybe the best stormwater control measure for their environment. Like I work a lot with the city of Philadelphia, and they, definitely prefer the vegetated approaches like rain garden type systems. However, the most frequently put in systems are infiltration trenches. And, if they're looking from a water quality standpoint, which one might be the one that they're trying to prefer. And so we see that there's these increased requirements to conduct monitoring and assessment. There's very little guidance, however, on how to actually do this. So there isn't a standard approach to really scoping out performance and monitoring programs. And this is what Elizabeth and I got to when we kind of came up with this question of really how many events do we need? So Elizabeth, please, next slide. So when we were thinking about this, it was, first it was almost like a kind of a cheeky question, like, well, how many events do we really need? But then we really started to think about it a little bit more, because we do know both of us collectively have been monitoring systems for well over 30 years. And we know the high variability that we see in our samples. There's storm to storm variability, there's seasonal variability, and of course there's annual variability as well in all of these different systems that we were trying to study. And you can look at the picture on the slide here, and we're just looking at total suspended solids, the event mean concentration, and the number of monitored events that you have. And you see that there's a big range of values on here. And when you look at a plot like this, now you have to make some sort of assessment on, well, how is this system behaving? And is this characteristic of how the system behaves? And obviously on this graph, we have quite a number of data points on here, which is great, but that's very expensive to get. So what if we had only been able to get 10 of these samples, or 20 of these samples, or 30 of these samples? Are they still going to be representative? Are we still going to see that the bulk of the values seem to be under 25 milligrams per liter, but we do have more than one excursion above there. We even have some in the 75 to 100 range. And so we want to figure out, how do we not just think about the average when we're looking at our data, but how do we think about the range of conditions that we're actually observing? While the average is informative in a way, we're often interested also in those higher values. And we're also interested in the lower values as well. And so what we wanted to do is we wanted to think about, how can we create a monitoring program, or how can we think about a monitoring program that is efficient, right? In that there's physical, logistical constraints on conducting monitoring. It rains more than our working hours, 9 to 5, Monday through Friday. So what are the physical constraints there? Then of course there's budgetary constraints as well. And then there could be some other constraints just in terms of, access to labs and things like that couldn't factor in. And so how do we balance all of those different constraints with really trying to represent the pollutant variability that we're really looking to kind of get out of a monitoring program? So Elizabeth, please, next slide. So what we came up with is using a data plan, and Elizabeth is going to go into all of the details of how we use data to help us really try to figure out what a monitoring program design could look like to adequately represent the pollutant concentrations that we see in different stormwater control measures. So what we wanted to do was we wanted to look at a couple of different pollutant types. And so we break them down into our standard categories. So representing our nutrients, we have phosphorus. Representing our metals, we have copper. And then we're also interested in solids. I did see a few of you in there were interested in bacteria. And what we pulled our data from the International Stormwater BMP database, and Elizabeth will get more into this, but the bacteria data just isn't at the quantity that we really needed to have any true statistical inference. So we also made some assumptions on this real data that we pulled and the concentrations that we had there. And then we also looked for a range of data within the data sets that we used. And so there were a prevalence of samples below our detection limits and then also above that. So our question today is getting at that how many. What we are not doing is we are not actually analyzing any of the concentrations. We're not making any sort of assessment or analysis on the performance. We're not trying to validate any of the sort of existing structures out there to comment on performance. And we are not designing, we're not actually designing the monitoring programs, but rather what we're trying to offer is some data that you could use to make a more informed decision about how you want to create your own monitoring program if you're in the business of creating a monitoring program. So that's really where we're getting at. Like, so if you were all thinking like, she's going to tell us exactly what we need, that is not what we're going to be telling you, but rather we're going to be giving you an idea of what you should be thinking about when you're putting a monitoring program together, and having an idea of the uncertainty and what you're willing to accept and what trade-offs are you also willing to accept. So with that, I'll turn it over to Elizabeth.
Thanks, Bridget. I want to add one more thing to what you just said, because I think this is a really important distinction in what we are trying to accomplish here. What we're, what the programs for validating performance claims for proprietary devices, are looking for data sets where you can prove a statistical difference between an inlet and outlet concentration. There are other statistical techniques out there that say that allow you to calculate in advance how many samples you might need to determine a specific level of difference between inlet and outlet, say a 25 milligram per liter difference between inlet and outlet. So those are very, very specific statistical outcomes that other techniques can be used for. That's not what we're trying to do. We're trying to acknowledge, like, BMPs are out there and they're performing how they're performing. What is that, right? What is the data set that we need to describe this general performance? Okay, so as Bridget mentioned, we wanted to start with information that was out there on very large data sets for stormwater control measures, inlet and outlet concentrations over a range of pollutants. And we assume, so we went to our favorite repository, the International Stormwater BMP database, to pull data on real data sets of SCM performance for suspended solids, copper, dissolved copper, and total phosphorus. So again, that's everybody always cares about sediment. Our dissolved copper is our representative heavy metal. We're using, when we looked at dissolved versus total, since the dissolved form is the form that really causes problems with aquatic toxicity. And total phosphorus, you're the Chesapeake Bay, of course, we're looking at phosphorus. So the data in the BMP database is organized according to US EPA rain zones. We thought that climate might be an important factor to consider. However, when it comes down to it, even though the International Stormwater BMP database is just a fantastic repository for data, it turns out there's a real dearth of very large data sets. And so we supplemented a couple of data sets from the National Stormwater Quality Database. And those data sets were really for Rain Zone 6, where I'm located in the arid Southwest. There's just very little data there. So our fundamental assumption is that these large data sets represent the true variability, or have captured the true variability for pollutants at a given site. Our large data sets we defined as having greater than having at least 15 events at either an inflow or an outflow. You don't have to have both. This is not a paired data study. So our data sets of large data sets, we just wanted to give you a kind of a very specific idea of how many data sets are available. Chesapeake Bay, according to the US EPA rain zones, is the Great Lakes region. Look, don't blame us for the rain zones, talk to the EPA. But just so you can have an idea, in the Great Lakes region, there are only 3 data sets for either inflow and outflow for TSS, right? 2 for dissolved copper, either in or out, and 2 for dissolved total phosphorus, in or out, right? Overall, not a lot of data available. And when we started to get into the analysis, one of our fundamental assumptions is that the data that's been reported is taken as our true values, right? The true representation. So we acknowledge that the number of data points in those original data sets, which we call the parent data sets, or we're going to call the parent data sets here, those original data sets, the number of samples there probably has an influence on how our outcomes go. And so if I break out a little bit further what the distribution of those data sets looks like, you know, sort of fortunately for the Great Lakes region, actually, we have the majority of the data sets that are there. Each one of those data sets has, you know, 31 to 60 data points. So that's actually quite a lot, especially compared to some of the other rain zones. But you'll see that there were no data sets over here in the really large categories, or in the reasonably small categories. So ultimately, we wind up doing a lot of consolidating of data. Oops, wrong button. So we take these real data sets, our parent data sets, and our goal is to try to figure out if we were able to conduct a smaller monitoring program and therefore save money and effort and resources, if we could develop a smaller monitoring program that adequately represented the real data set, how many samples would that be? So we use statistical methods and a whole bunch of scripts in Python because we have great support from a couple of our tech staff, a master's student at Villanova, Matt McCauley, and a research tech at Squirt called Emily Darren. And they're excellent programmers, and they helped us writing scripts that basically we start with our parent data sets, say a parent data set that had 85 storm events, and using automated processes in Python's created data subsets that represent hypothetical monitoring programs as if only 25 events were sampled at that site, or maybe 15 events were sampled, or 5. Actually, we looked at data subsets of 5, 10, 15, 20, and 25 hypothetical monitoring events. And for each one of those hypothetical monitoring events, we repeated that extraction, that creation of the data subset 500 times. So for our 85 events over here, there are 500 monitoring programs that only sampled 25 events. There are 500 monitoring programs that only sampled 15 events, and so on. Is that clear? That's kind of an important step for how we're doing the analysis. So if you have any questions at any time about the methods we've used or any of our assumptions or whatever, please drop them in the chat, and David's going to interrupt us so we make sure that we're keeping everybody with us. Okay, so we've got all these, 500 times 5 is 2,500 data sets to work with. How are we going to compare them all? So it turns out that the distributions of these data sets, the statistical distributions of the parent data sets, were all over the place. There wasn't one single type of distribution that describes all these parameters. And comparing data sets by distributions is a really nice kind of comprehensive way to do it. But we can't do that directly because all of our distributions are different. However, we realized that we can use some representative values from each distribution type that serve as the basis of comparison. And for that, we chose percentile values. So a percentile value, the value itself is a concentration. And a percentile value, sorry, my phone is buzzing over there. I had to move it off the desk because my computer would start to buzz at you all. So a percentile value gives us the fraction of data that's at least equal to that concentration. So the median value is the 50th percentile. In a normal distribution, this is also the mean value. Your 50th percentile distribution means half of your data is that concentration or less. the 25th to the 75th percentile values, so 25% of the samples up to 75% of the values, are typically referred to are what's considered the interquartile range. The vast majority of the data in any data set is going to be within the interquartile range. So this really follows the range of your very typical values. And your 10th and your 90th percentile values are extreme values, extremely low or extremely high. And you might be concerned about extreme values in a monitoring program because your extremely high values may cause an acute problem or an acute response in the receiving water. Your extremely low values may particularly be of concern for effluent values. How clean is the water that's discharging from an SCM? Where you have nutrient sensitive waters, trout waters, or where you're trying to meet numeric effluent limits. So we can identify these sort of anchor points that describe a distribution regardless of the type of distribution, and that provides us a consistent way to compare. Okay. So our next step then was to we want to quantify the ability of these hypothetical smaller monitoring programs to represent the real range of pollutants measured, right? That parent data set that we extracted from the International Stormwater BMP database and the NSQD. We quantified uncertainty as the relative percent difference at each one of those percentile values. So there's 5 percentile values. So there are 5 comparison points across the distributions for how well our hypothetical monitoring programs are matching those real monitoring programs, or the percentile values for the real monitoring programs. And the difference there is what we're calling the uncertainty. Remember, we have 500 hypothetical monitoring programs for each monitoring program size. So we've averaged those values over the 500 hypothetical data points at each data subset size, right? So lots of consolidation. So it's a lot of numbers come out, right? And you do this site by site and for inflow and for outflow. So I want to give you an idea of the type of information that we bring out of it and how we start to consolidate the information. We visualize the results in a heat map. So our heat map shows us, so across the bottom here, and this is just for way of an example to demonstrate the types of outcomes that we have and the kind of information that we're going to consolidate. So each one of these columns is a real monitoring program. So we have 3 monitoring programs. One has 181 data points in the parent data set. One had 43 and one had 84. And going up, the rows represent our hypothetical, the size of our hypothetical monitoring programs. And the number in each box in these rows gives us the average relative percent difference, or the average, what we're calling the average uncertainty for the hypothetical monitoring program to represent the real concentration. In this case, we're looking at the 50th percentile or the median concentrations. Okay. So the key thing here is there's no right or wrong. We are just, the result is how different is the hypothetical monitoring program to the real monitoring program. And the key question for you as program managers is how much uncertainty is okay for your program. So in this case, and so we've color coded it in a heat map just to make it easy to kind of jump out. And you know that the way I would read this is, you know, 4, 5, 6, 9%. We've got less than 10% uncertainty for any of these monitoring programs that have 10 to 25 sampled events, compared to there's less than 10% uncertainty for average concentrations compared to a monitoring program that had 43 real events. As you might expect, you know, where you had 181, a monitoring program with 181 samples, and we're only representing them by 5 samples, we had a much larger uncertainty in being able to represent that true value. Bridget, do you think, okay. All right, so then when I expand,
sorry, it took me a second to find my mute button, right?
No problem.
We're still working on this. One thing I would say is, you know, we've gotten this question before of when we say true value, it is the parent data set, because like, is that even representing a true value? So we are making the assumption that that is our true value. You know, we can have a philosophical discussion on this, but just something to sort of keep in mind that even when we're comparing against a true value, there is still perhaps uncertainty even if with that as well. So I just wanted to make sure that's clear, that there can be some compounded uncertainty.
Okay, so the graph in the middle here is that exact same graph you just saw, but now I've expanded it out to include the interquartile range for each one of these. And you can start to see there's some differences that come up when you're talking about different percentile points or different points along the distributions. And in particular, in this case, when remember the lower your percentile value, the lower your concentrations that you're comparing are. So we're getting down towards lower concentrations. And in this case, at this particular site, there really did seem to be an effect of our sampling program, a hypothetical sampling program, smaller sampling program, being able to represent well, or introduces more uncertainty in reflecting that the true values from the parent data set once you get to lower concentrations. And we're going to dive into that a bit more. Okay, I think we've been repeating ourselves a fair number of times for this explicit point that there's really just a very limited amount of data. Our real data sets, those parent data sets that we took from the databases, do show a lot of variability, but no clear trends in variability, meaning that the inflow variability is on par with the outflow variability at a given site. And so in terms of how variable are these concentrations that we're trying to reflect with our monitoring programs, we see there's no trend across the board. We can't say one pollutant is more variable than another, or one rain zone is more variable than another. That doesn't jump out at us. We also find that the relative range of concentrations is reasonably consistent. In other words, TSS varies over an order of magnitude at a given site, at all sites. Total phosphorus ranges over a couple of milligrams per liter, pretty much at all sites. And dissolved copper ranges over a much narrower range. That's just the way it goes. And what we see is that relative range of concentrations at almost across all the sites is very consistent. And the very bottom line is there's just an extraordinary limitation on the amount of data sets available where there are at least 15 monitored events. This resulted in us grouping our inflow and outflow data and grouping all the rain zones together in terms of proceeding with this analysis of uncertainty. Okay, so how do we take, now the real question is, how do we take all these different heat maps? So we've got 27 heat maps for total suspended solids, 23 for phosphorus, and 11 for dissolved copper. How do we take all these different heat maps and consolidate them to try to get some general meaning out of them? So as we said, we've consolidated everything by rain zone and by what we're calling flow type. What we have kept distinctions in are the type of pollutant and how the size of the parent data set, the real values, the true values. So what we did was consolidate all these heat maps into a family of curves. And the point of this diagram here, or the slide here, is to explain how to interpret the family of curves. So I've just chosen the 50th percentile or median values family of curves for TSS. What we see across the bottom, the x-axis now is the number of events in the data subset. So that's our hypothetical smaller monitoring program. And along the y-axis is the mean relative percent difference, our estimate of uncertainty that results from either one of these smaller monitoring programs. And for convenience only, the dashed lines go between the 10 and 20% relative percent difference or uncertainty. And that's really just to help you read the plot. And then each of the colored lines with the different markers represent the results for according to the size of the real data set, the parent data set. So what this says is if I had, for example, if I monitored 25 events, we can see that for parent data sets of 15 to 90, up to 90 data points, the median value predicted by any of those smaller monitoring programs would be within about 10% of the value that you would get if you had sampled 90 events, right? If we instead monitored only 10 events, a monitoring program that sampled only 10 events would get us within about 20% of the median value of a monitoring program that had sampled anywhere from 15 to 90 events, and would get us within about 40% of the value, the median value determined from a program with over 90 events. So this is an important point. I want to pause for a second and make sure that you all you're following how we're interpreting these graphs. I don't know, I don't know if you can do reactions. Could we see some thumbs up or something? I don't know if you're able to do that, but are there any questions on how to interpret these data? Because then we're going to dive into the data. Pause for a second. And remember, there's no right or wrong answer here, right? The outcome is how much uncertainty. Okay, thanks, Thomas Jones. The outcome here is how much uncertainty is okay for your program. Great, thank you, Scott. Okay, good, we've got some positive stuff. Amy, great, awesome, then I'll move on. Okay, so the first outcome here is, just checking time, is that for TSS shows the greatest range in pollutant concentrations in the real data sets. And what we see here is that the family of curves showing the uncertainty or the relative percent difference for each one of our percentile values from the 25th to the 75th percentile, that interquartile range, they overlap. So a monitoring program that has anywhere from really 15, I messed up that top box there, anywhere from 15 to 90 events, anywhere in there is giving us the same kind of uncertainty when we represent them with smaller sample sizes. So if your monitoring program gives anywhere from, your hypothetical monitoring program has 5 to 25 events, is going to give you about the same relative uncertainty for that interquartile range. And just as a point of reference, you know, we need at least 15 events to monitored for less than 20%, about 20% uncertainty. So this is where you have a very high range of variability in the real pollutant concentrations. Where you have a lower range of pollutant concentrations, which was the case for dissolved copper, it's slightly different. Our monitoring programs of 5 to 25 events, they're overlapping. Our uncertainty is overlapping for the families of curves from 31 to 90 events. So for your median or greater concentrations, you can represent them pretty well with smaller monitoring programs. But this magic number of 15 kind of came out, it jumped out at us again. Again, we needed about 15 events for corresponded to about 20% uncertainty. And again, we're not advocating 20% uncertainty. This is more just for pointing it out. And it seems like it was interesting to us that it kind of converged at the same, around the same values. We do have a significant impact of low concentrations on the analysis, or the proportion of samples that are very low concentrations, very specifically concentrations below the analytical detection limit. So how to represent or how to report data below detection limits is kind of all over the place. We adopted for this analysis the convention that's used in the International Stormwater BMP database, and we applied it to the 2 data sets that we also borrowed from the National Stormwater Quality Database. And that assumption is that where a sample is reported as being below a detection limit, we use the value of half the detection limit. So we had to substitute a value, right, for a missing value. Bottom line is assigning values for non-detects disproportionately influences the 10th and 25th percentile values, particularly down here where we have a very high range of concentrations, namely our TSS data. So the key thing here was we did have a couple of data sets that had no samples below the detection limit. All samples were above detect, and that's the orange line. And what I want to point out here is that between the orange line and the green line, the greenish line, the olive line, is 1 to 9% of the total sample sets being less than the detection limit. This is of the parent data sets, the original data sets, the real data sets. Basically, as soon as you have 1% of your samples below detection limits, all of a sudden you get much, much higher uncertainty in the ability for a smaller monitoring program to reflect the real concentrations. And it's a more pronounced effect for TSS than copper, because TSS falls along a much greater range of concentrations to begin with. So there are a couple of things that come out of this. One is, if you're worried about sensitive waterways, you really want to be aiming for understanding how clean the water gets. And if you're evaluating effluent concentrations and you have a BMP or an SCM that works really, really well, you might bias those results. So ultimately, how missing data are handled emerges as a really important factor in this analysis. So at the end of the day, we've come up with a method for recommending a monitoring program size that's informed by real data analysis. So we assume that our monitoring data sets that have at least 15 events represents the true range of inflow and outflow pollutant concentrations. As Bridget said, we could talk about this all day, and Bridget and I do talk about this all day. And but this is about data availability. This is partially about data availability. Okay? The good news, I think, was that a hypothetical monitoring program of anywhere from 5 to 25 events generates similar patterns of relative uncertainty that RPD, the relative percent difference, for the interquartile range, right? The major proportion of your data points will be reasonably accurately reflected, or I'm sorry, I'm not making a judgment call. The patterns, whether you have 5 events to 25 events, the patterns are overlapping there, and you get a pretty good representation of the interquartile range in there. I think I messed that. I didn't say that correctly, but I'll go on. The larger monitoring programs are definitely needed if you have a specific interest or need to characterize your extreme values, either at the very low end or the high end. And that's just simply that these are more rare kind of occurrences. So you just need more opportunities to sample to be able to reflect those. I've just talked about our proportion of samples below detection limits and how they're really, that's an area that needs further study or serious consideration or real interpretation for your own context. But the bottom line is, we've got a method here that's informed by data and how to develop a monitoring program to represent the range of values that you should expect from an SCM. But it's up to you all to establish an acceptable level of uncertainty to be able to implement this kind of analysis. Oops, wrong button. So you can do this yourself. If you have data from your own monitoring programs, our code is up on GitHub, or send it to us. Send it to us and we'll do it for you. And if we can use it to include in our analysis of how the method works. And really, we would love for everybody to share your data in the BMP database. It's really a great repository that enables this kind of analysis and more, but it's limited by how much data are submitted. So we are writing this up into a formal journal paper, an academic kind of journal paper, and that's in progress. With that, we are happy to take any questions. Want to acknowledge Emily and Matt again, because without their number crunching skills, we would not be able to do this kind of analysis. But with that, we're happy to take any questions.
Great, thank you so much, Elizabeth and Bridget. Really interesting stuff. And I know that sometimes it can be tricky, especially to communicate when you're dealing with that much data and that many numbers and things like that. So if folks have questions, please go ahead and chime in the chat or the Q&A. I had one, sort of question for you, maybe to get things started. And, for folks that are kind of looking for a rule of thumb or, a back of the envelope way of kind of doing this if they don't have all of the data available. I was wondering if there was anything that you could sort of recommend on that front, or maybe if you've done some sort of optimization or anything like that of, these data, if there's a certain, best bang for your buck in terms of aligning your smaller monitoring program with a parent data set or something like that.
Well, I think what you've just said is the exact reason that we did the analysis. Was the real motivation was that a lot of programs don't have access to data. And so we thought, well, what's a good representation of BMP data or SCM data? And that's why we went to the BMP database. So the idea was that if you don't have your own monitoring data, you could use this one. And just by, our review of the data sets that we use said, okay, these are highly variable data sets. We looked at a bunch of different kinds of pollutants. And the fact that those families of curves started to overlap gave us real confidence that we were converging on pretty good numbers, or a robust kind of analysis.
And I would say, just adding on to that, like if you're starting a monitoring program at this point, and sort of like overwhelmed by what to do, where to do it, and how to do it, and how many of them to do it, it's no data is better than, nope, wrong. Some data is better than no data. But I would suggest being really thoughtful with where and how you monitor. So, picking a system in your portfolio that is one of those sensitive systems that you really want to make sure, like, not necessarily, I would almost encourage you to do more different types of SMBs or SCMs in your portfolio in targeted locations and getting more data on each one of those versus trying to get data from every single one of your systems in your portfolio, where you might only then be able to get 3 or 4 data points. I think it'll be more informative to you to focus in on a targeted number of systems that you could do more, maybe something along the lines of 15. And then that would give you an idea of how the watershed is behaving from your inflow. It would give you an idea of how the systems are performing from an outflow perspective. And that would be my suggestion there, is if you are in this resource limited environment, how to maybe approach this and how to take this data and inform that.
Great. One last one that we sort of talked about a little bit offline, but and it's a little bit outside of this specific research, but I wondered your thoughts or your recommendations for folks if they're interested in monitoring or developing a program for a constituent or a pollutant where there is not a lot of data, where we are data limited and we don't have a lot of parent data sets available to them, whether it's bacteria or something like that, some sort of emerging pollutant. Are there any sort of either resources or kind of guidance that you provide to those folks, or is it just kind of a matter of we need to start collecting data somewhere and then we'll start to compile it over time and it'll add up until we can do this sort of analysis?
That's a good question.
Yeah. Yes, we just need more data.
Yeah.
That can be the answer. That's totally fine.
I think especially with, sorry, go ahead, Elizabeth.
Well, I was going to say emerging contaminants get into a whole other, I mean, you're in a whole other ballgame there. The thing about emerging contaminant, the reason that we have data for nutrients and metals and TSS is because because the NERP study in 1981 identified those contaminants as prevalent in stormwater. And that's what has really dictated where the funding goes for monitoring programs. The fact that we now have all these TMDLs for all sorts of other contaminants has not caught up. The funding cycles haven't caught up to the TMDL identified needs. And so that's a different kind of problem. And ultimately monitoring is driven by funding and who wants to know what. So chlorides. Yeah. So chlorides look to the northern states. The University of New Hampshire's Stormwater Center has been doing a bunch on chlorides. Look to monitoring from northern states about chlorides. Definitely not Southern California, I'll tell you that much.
And the tricky thing with chlorides is they're conservative. So, like the analysis that we did is just going to tell you like how many are representative, but it's not necessarily going to help you with that performance assessment piece because of, like just from my own research at Villanova, what we see is there's very little change in chloride concentrations in to out. And I could have 10 samples tell me that, and I can have 100 samples tell me that. So it also like think about what the goal of your question is. And I think that might also help you, whether it's like this type of analysis or, what other way might you think about approaching that monitoring is really like, what is the goal of the question you're trying to answer?
Yeah. And that was one of the things, we said we were not trying to achieve with this analysis was designing monitoring programs to answer unique questions, but defining your goals for monitoring before you start is absolutely key so that you're collecting the right data. Coming back to the emerging contaminants, because they are emerging, I hate to say this, but you got to do your legwork and find the experts, right? And they might not be in the BMP field as yet. Bridget and I were experts at figuring out how to collect data, with the physical systems that we're working with. We're really good at it, and it's really hard. But I'm not an expert on microplastics. I'm not an expert on PFAS, but I know where to find them. And I'm going to go sit down and have a conversation. I'm going to go find those experts. Fortunately for me, there are a few of those within my organization. And I'm sitting down with them and saying, here's the system I have. Tell me about the pollutant. And we'll have a conversation together about how best to develop some methods for monitoring and analysis, because it's definitely going to be different than what we do for our conventional priority pollutants.
Great. Well, maybe I'll start teeing up webcasts with experts in microplastics and other contaminants.
Yeah,
so.
I can help. I can point you to a few of those people. My agency, the Southern California Coastal Water Research Project, has just developed the first thresholds for drinking water quality for microplastics for the state of California. And that's the EPA is picking that up to adopt that, roll that out across the country. And so we're working with, we have the experts, and we're working in a consortium with a bunch of other researchers to go from, now here are the thresholds for human health effects to branch that out and to start to develop methods for how to sample and analyze, because it's very expensive. I can tell you that. I've seen how it's done. It's very, very expensive at the moment, but they're working on developing those methods to make them more accessible.
Well,
I
thank
just
you
want
so
to make
much.
one more comment. Sorry,
Oh, go ahead,
quickly.
Bridget.
I saw that the comment from Scott about chlorides are starting to rise in the DC area. And I would also be curious, are they rising because of road salt applications, or are you starting to see some saltwater intrusion in certain areas? And so depending on the reasoning for the rise in chlorides of what you're observing is also, I think, going to help dictate how you would go about thinking of a monitoring program. Main assumption is road salts, yeah. So definitely the northern, that's what we've been working on.
Well, thank you, Elizabeth. Thank you, Bridget. This was really informative, and I really appreciate your time. Before you leave, I did put the evaluation survey in the chat, as well as our stormwater professional survey again. So, put it up in your browsers, leave the tab up if you don't have time right now. I would really appreciate it. But thank you both again, and be on the lookout, folks, for the recording and the slides if you want to share it with any colleagues or pass it around, or you had to drop off early or whatever. Obviously, you're not still here, but you can see this later. All right. Thanks, everybody. Have a great rest of your day and rest of your week, and hopefully we'll catch you at our next webcast, which is coming up next week.
Thanks, everyone, for participating.
Thank you.